You ready to proceed? I sure am. Here we go. We're going to state the critical numbers of this, determine intervals of increase, decrease, or concavity, and state if each critical number corresponds to a relative max, minimum, or neither. You've done this, but now the problems are getting a little bit trickier. So let's move on. First thing I should do is take the derivative. So let's do just that. First thing I really should do is write it as x to the 2/3 minus x. That's going to help me take the derivative. It's going to make it a little bit easier. So now we're ready for a derivative. 2/3 x to the negative 1/3 and then minus 1. There we go. So as I look at this, I can think, oh, let's rewrite it. If you want to leave it like this, you can, but it's going to be really hard to identify what needs to be identified. So this is 2/3. X to the 1/3 is a cube root, and it is in the denominator because it's negative, minus 1. Okay, we're going to set this equal to 0, and we're going to solve, because that's what we do. Critical numbers occur where the derivative equals 0 or where the derivative doesn't exist. So we'll set that equal to 0. We'll move the 1 over. We'll cross multiply. It's going to be great. So look how much fun I'm having. It is fun. So 2 over 3 cube root of x equals 1. We'll cross multiply. And am I on camera? Yeah, I'm on camera. I'm on screen here. So 2 equals 3 times the cube root of x. We'll divide by 3. We have 2/3 equals cube root of x. And yeah, making sure my work is good. Multiply this, bring it up, divide by 3. There we are. We're going to cube both sides. I'll cube this. I'll cube this. 8 over 27 is x. Found it. Great. Wonderful. Now, here's the deal. We just found a critical number. Are there more? You might say, no, that's it. We've solved it. I hear you. Are there any places where your derivative does not exist? Yes. X can't be 0, right? Now, we could make an argument, and we'll deflate this argument in just a second. We could make the argument that says, well, x can't be 0, clearly, so the function's discontinuous at 0. No, look at the original function. I could plug in a 0, we're good. So if you're saying, oh, well, I can't divide by 0, x can't be 0, then, can't do it. Wait a minute. The function is continuous at 0, but it is not differentiable. The function, and off the top of my head, I don't know what this function looks like, but there's a really good chance that it's going to be one of these situations, and that, like, the little birds that you draw in the sky, that is going to be where x equals 0. It's some situation kind of like that, where you have a very pointy point. Not a technical definition, but anyway. All right, here we go. X equals 8 over 27. That is a critical number. And also x equals 0 is a critical number. That did not come from solving it. It came from looking at the derivative, this or this. This is a little more practical to look at. And saying, all right, is there anything x can't be? I can't divide by 0. If x was 0, we'd be dividing by 0. There we go. So both of these are critical numbers. Both of these are critical numbers, abbreviating again. And this critical number came from solving. And this is where the derivative does not exist. Okay? Those are two separate ideas. They came from two separate places. Now that we have that in mind, let's draw our number line with some sign analysis with a very loud marker. 0 and 8 over 27. Okay, we're going to plug numbers into the derivative, and we are going to do this in our head. Watch out. Okay, let's first of all plug in an enormous number, like 1,000,000. Okay, you plug in 1,000,000. The cube root of 1,000,000 is big. You have 2 over 3 times enormous. This is really close to 0. So big number makes denominator big. 2 over enormous is very close to 0. 0, essentially, minus 1 is negative. So for large values, or basically any value larger than 8 over 27, you're going to get a derivative that is negative. So the derivative is less than 0. Shall I do it again? Shall I pick a number that's not like some abstract, like a zillion? Okay, let's pick a number that you can take the cube root of, but it's kind of reasonable to do. Actually, 1. 1 works beautifully. The cube root of 1 is 1. 2/3 and then the 3 times the 1. So 2/3 minus 1 is negative. There you go. All right, let's pick a number. I'm going to save the hard one for last. Let's plug in a negative number. You plug in a -1. If I plug in a -1 right here, I have the cube root of -1. So I have 2 over 3 times the cube root of -1 minus 1. Our instinct is to say, oh, it's imaginary. It's not. It's a cube root, not a square root, or not an even root. So this is totally doable within real numbers. So 2 over 3, cube root of -1 is negative. We have -2/3 minus 1. That's definitely negative, -5/3 to be exact. So f prime is indeed negative. Okay, good chance that one in the middle, that interval in the middle has a positive derivative. Let's find out. And we're going to pick a number in between 0 and 8 over 27. What? How are we going to do that? Well, and we're going to do it without a calculator. I've done this problem for years, and I have found the best number to pick is a number that is a perfect cube, because we need to take a cube root of something. And I'm going to go for something that may not seem obvious, but as soon as I say it, you'll say, oh, well, yeah, that makes sense. A number between 0 and 8 over 27, 8's a perfect cube, 27's a perfect cube, that works would be 1, this little number right here, 1 over 27. 1 over 27. Let's do it. So I'm going to pick 1 over 27. I'm going to plug it in. So 2 over cube root of, 3 times the cube root of 1/27 and then minus 1. The cube root of 1 over 27 is 1/3. So I have 2 over 3 times 1/3 minus 1. 3 times a third is 1. I have 2 minus 1. I get a positive number. So plug in any number, and I plugged in a number that's fairly obvious once you think about it. I get positive. Okay, we've been through this, so we now know the intervals where the function is increasing, decreasing, and we can also look at that, use a little bit of logic, and determine whether these points correspond to maximums or minimums. All right, here goes. Let's start writing some stuff down. I'll keep writing in red. We have a function that is decreasing on the interval from -infinity to 0. And also, technically the mathematical word would be or here. 8 over 27 to infinity. Okay, increasing on the interval. Let's make that work. There we go. Spell it correctly. The spell checker was not working. There we go. 0 to 8 over 27. Now, because, and we've been through the logic, I'm not writing it out. If this was free response, we need to write it out. We would be like, oh, this is what I'm going to do, and this is why I'm going to do it. And I'd love to. We did that on the first 2 examples. I'm going to move on for this. Minimum, maximum, and here's why. And again, I'm not writing it down, but here's why. We have a minimum at x equals 0 because the derivative is negative, then positive. The derivative transitions from negative to positive at x equals 0. That means the function was decreasing, then increasing. That had to be a minimum down there. So we have a relative minimum at x equals 0, and we're going to have a relative maximum at x equals 8 over 27. And here's the reason, not writing it down, but because the derivative transitioned from positive to negative. Putting it another way, the function transitioned from increasing to decreasing. All right, we're going to do one more problem, and it's a doozy. It involves logarithms and the product rule. It's beautiful, absolutely beautiful. So I'm just going to erase a little bit here just to give myself some room to start, and then I'll erase more as needed. There, I'm going to leave that there just to make you angry. Like, why isn't he erasing that? X ln x over 4. X natural log of x over 4. Ooh, I got the weak marker. Okay, let's actually talk about the domain on this one, and that's going to be very important. On every function we've done so far, the domain was all real numbers. Like, there is nothing bad about plugging in any x value for any problem we've done so far. The one with the cube root might have looked iffy, but you can plug in negative numbers for cube roots. It totally works. It's great. It's fun. Do it all the time. However, if you're going to stay in the realm of real numbers, I'm still going to leave that just to drive you nuts. If you're going to stay in the realm of real numbers, you will never take the log of a negative number. You'll never take the log of 0 either. So I cannot go domain-wise past 0. Cannot include 0, cannot go past 0. So whenever I do my number line, I'm not going to draw arrows and be like negative infinity to infinity. No, 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 no. That was awkward. There we go. What I'm going to do is start at 0 and move up, because I cannot take the log of 0. Try it. Sometime your calculator will explode. Can't take the log of a negative number. It's imaginary if you do. So this is what I'm dealing with. I put an open circle because we cannot include it. Eventually we'll put some stuff on there, but that's what my number line is going to look like. 0 is the furthest to the left I can go, not including 0. Some teachers do this instead. They'll put it like interval notation, like a little parenthesis. To me that looks like an arrow, so I'm not going to play like that. So zoom, there we go. Looks like a double O, but whatever. All right, derivative time. Let's do it. Product rule, I think that's obvious. So here goes. Product rule. F prime, putting a 1 just to hold its place. G plus F, G prime. Oh boy. All right. Product rule with a chain inside. This one can be done in our heads. I think I should erase something. Let's erase the whole thing. This one could be done in our heads, but it gets a little bit iffy. I want to write this one out because there's so much simplifying that happens in the process. If I do too much, I found that students get lost in this one. So just very briefly, I'm doing F prime G, that's the way I explain it, plus F G prime, that's going to happen here. And I'm going to say, and again, if you're watching other older videos of mine, you would say, oh, well, this is F, but this is F. No, that I'm just using the F and the G as placeholders in the product rule formula. I do the same for chain, do the same for quotient. So just ignoring the fact that we're dealing with F, the problem is F. I'm saying this is F, this is G. So this is F, this is G. And then in the process of that, I need to take the derivative of this. So I'm going to say, well, what I'm really dealing with, and I'm about to figure out this one. Okay, I'm pausing the product rule to do chain. So I am really taking the derivative of this, and I'm going to do chain. So we're introducing F's and G's again. Sounds confusing. It's a notation that works for me. So the biggest thing happening is that somebody got logged. The derivative of a log is 1 over whatever. Who got logged? X over 4. Good to know. If you want to, this is going to make it a little easier to understand. Treat that like 1/4 x. Same thing. The derivative of that would be 1/4. So when I do the when I do the chain rule, this is going to go in the place of that, and then I'll multiply by this. So what's about to go right here is 1 over 1/4 x times 1/4. What in the world? What in the world is going on here? Okay. A lot of stuff we could do, a lot of ways I could explain it. I'm actually just going to go for something that's obvious, but maybe not so obvious. This 1/4 and this 1/4 in the denominator cancel, and I'm really left with this beautiful thing right here, which is 1 over x. Now, there are other reasons why this cancels. Technically, I could reciprocate this, bring a 4 up. This 4 cancels with that 4. It's great. It's wonderful. But really, I'm just left with 1 over x. Okay. Looking at this, you're going to see that something's going to cancel real fast. Those x's right there. So I'm going to erase this. Pause the video if you need to. If you want to watch the chain rule with a red marker, if you're into that sort of thing. It's one of my hobbies. I'm going to cancel this x with that x. So just for the sake of simplifying, we have natural log of x over 4 plus 1. Okay, good to know. Good to know. Whew, all right, let's keep having some fun with this one. I want to know where this derivative doesn't exist. Okay, critical numbers happen where the derivative doesn't exist, and also happen where the derivative equals 0. We'll tackle in a minute where the derivative equals 0. In the meantime, the derivative doesn't exist for values that are 0 or negative, because you can't take the log of 0, you can't take the log of a negative number, not if you want to play with the real numbers. So we actually already discussed that. That's not an issue because I'm looking for specific x values where the derivative does not exist. I'm not talking about an entire interval, okay? I would be like, oh, well, the derivative doesn't exist at 12, you know, yeah, that's what I'm looking for. I'm not looking for entire intervals that I would exclude. Those aren't critical numbers. Those are tragic ends to a domain, all right? What I am also going to consider is where the derivative equals 0, and we will solve that. So, natural log of x over 4 equals -1. Solve that. Oh, you can't solve it because logs can't be negative. You can't take the log of a negative number. You can with imaginary numbers. But you can't take the log of a negative number, but a log can equal a negative number, and here's how. There's a little e down here. E to the -1 equals x over 4. We'll solve it. Don't make it harder than it is. E to the -1 is 1 over e equals x over 4. Multiply by 4. 4 over e equals x. That's it. This, my friends, although we may not be friends after this problem, the friendship is over. This is our critical number right there. That is our only critical number. So we will come over here with a marker and say 4 over e. Now before you grab your calculator, what's 4 over e? We're going to get a decimal. Done this problem numerous times. We can do it without a calculator, trust me. I'm going to plug numbers from each interval into the derivative, and we're going to figure out if the derivative is positive or negative and do our little thing that we've been doing, but we can do it without a calculator. It's splendid. You're going to love it. So I want to plug in a number in this interval that I can basically, well, you'll see. All right. Sometimes you have to get creative with these things. I'm gonna find a couple numbers that I can easily plug into my derivative. And the number I choose from this interval is, check this out, this is beautiful, 4e. Watch this. If I plug a 4e right here, 4 will cancel, and I'll be left with the natural log of e, which is 1. And then I'll have 1 plus 1, which is 2, which is positive. I'm going to write everything down. So I'm going to pick a number that is bigger than 4 over e. 4 over e is, okay, 4 divided by about 2.7 is small, right? 4e is larger. I'm going to find out what f prime of 4e is, and when I do, plug it in. What if I don't think like that? What if maybe it's calculator active and we could do it another way? Maybe you could graph it. You could kind of see what it does. But I'm just teaching you things to look for. So if this doesn't go through your mind yet, that is okay. I'm teaching you things to look for, ways you can say, oh, 4, let's try to make it cancel with that 4. I don't want that 4 there. Just pick a number. 4e, 4 times 2.7, that's much bigger than this, which is a little less than 2, okay? All right, let's do this. F prime of 4e, that would be the natural log of 4e over 4, and then plus 1, which is, again, cancel, cancel. Natural log of e plus 1. The natural log of e is a question that says e, understood e, to what power will give me e? That's 1. 1 plus 1 is going to give me 2. I don't care that it's 2. I care that it's positive. So in this interval, the derivative is positive. If the derivative is negative in this interval, then we have a minimum at 4 over e. What number are you going to pick for that one? Watch this. Watch this. It's so good. This is so good. I'm going to pick 1 over e. It's going to get a little tricky, but it's going to work. Okay, let's plug in 1 over e. So 1 over e goes into the derivatives, and I'm going to have the natural log of 1 over e over 4. And then we're going to add 1 to that. And it's going to get a little sloppy, but we'll deal with it. Okay, check this out. Natural log of, I'm going to call it 1/4 e to the -1, and then plus 1. It's the same thing. Okay, this e is in the denominator. It's really e to the negative 1. This is really 1/4. It's the same thing. It really. Do you need to see it? Yes? Briefly, if you do, feel free to skip the next 20 seconds or so. If I had 1 over e over 4, then I would really have 1 over e divided by 4 over 1, which is 1 over e times 1/4, which is really 1 over 4e. This e can come up and it becomes 1/4 e to the negative 1. All that, you'll get fast with it. You will. Trust me. I hope so. I believe in you. Okay. Back up if you need to see that again. I'm panicking a little bit. I am, but I'm not. And here's where I'm panicking but not panicking. I have a function that I have a derivative that I can't quite evaluate. Let me show you what I'm talking about. I have the natural log of 1/4 e to the negative 1. Here's what I'm going to do. Check this out. Using some properties of logs. This was a fun one. Man, I love this problem. Natural log of 1/4 plus natural log of e to the negative 1 plus 1. It's the same thing. Back in the day, you learned that if I have log plus log, they have the same base, and they do in this case. If I have log plus log, put them together because of the properties of exponents. If I have log plus log, put them together and multiply. Okay, totally works. You can break them apart as well. So that's what I'm dealing with. So I have the natural log of 1/4 plus natural log of e to the negative 1. This is a question that's about to get answered as I say the question. The question is, e to what power will give me e to the negative 1? E to what power is equivalent, check this out, e to what power equals e to the negative 1? Well, then the answer to the question is negative 1. Negative 1 plus 1. Cancel, cancel. I'm left with the natural log of 1/4. So now the question is that positive or negative? I'm tempted to say, oh, that looks positive to me. Is it? E to what power will give me 1/4? I don't know, but here's what I do know. E to some power gives me 1/4. I'm walking you through a lot of logical things. If this problem feels overwhelming, if you would not have thought of this, if you're like, my mind doesn't go there, my mind didn't used to either, I'm showing you little tricks. This problem is so full of fun little logarithmic things, I just couldn't leave it out. It was just not in my heart to do so. Let's move on. E to what power gives me 1/4? Knowing that e is about 2.7, we'll just, for our purposes, we'll call it 2.7. That is a horrible rounding, but there we go. 2.7 to what power gives me 1/4? 2.7 just got smaller. Therefore, its exponent must be negative because that would reciprocate it and put it in the denominator. Therefore, this is a negative. All that without a calculator. Wasn't that fun? Yes. Okay. Found our critical number. We have a whole lot of work showing there. We're going to write a final answer in red. I'll try to squeeze it in on the board over down there. So we have an interval of decrease, interval of increase. So decreasing on the interval from 0, not including 0, don't put a bracket on that, 0 to 4 over e. And increasing on the interval from 4 over e to infinity. You can plug in any number beyond 0 and it will work. Any positive number works. And we have a maximum or minimum. Take a moment, glance, look. Maximum or minimum? Okay. Minimum, the function decreases then increases for the sake of free response. I'm going to write that out one more time. I have skipped it in previous problems. Let's do it on this one. Video is already, what, 24 minutes long? Let's just keep going. It's like an episode of a sitcom. Only without the jokes and with lots of math. All right. X equals 4 over e corresponds to a minimum, relative minimum. Get my head out of the way here. Because the derivative changes. I don't want to say it changes signs. That's not enough. It changes from negative to positive. Therefore, and I'm extrapolating on what I wrote. That is sufficient, but I'm extrapolating on what I wrote. Therefore, the original function, because the derivative derivative negative positive, the original function decreases, then increases. All right, sitcom is over. Come back next week and you'll see what happens with logarithms. All right, thank you for watching. I don't know why I said that.